work, so it's going to be on the next one. The other thing that I was going to mention is the date for the midterm. It appears to be November 5th, at least for now, Monday. Midterm. Okay, so we'll have time to talk about the details. At this time, as I was saying, we are studying composition. It's a big topic and complex, and a lot of trouble understanding compositions as opposed to algebra of numbers. And the one reason is that probably, in my opinion, is that is overemphasis on graphs. And as you can see, it is probably a good idea to have this picture first in your mind when you think about compositions. That is the arrows and how they aligned, and you proceed from one to the next. So when you know your destination, that becomes the initial point of the next arrow. That's you know your final destination. The second point of view, which is I find very helpful with this. So look, this is a picture of what if you try to carry out consecutive compositions using graphs. You will have two graphs, and you have to somehow align the output. So you'll have two axes, x and y for the first function, y and z for the second function, and then you have to somehow progress as an intermediate step, getting from the y-axis on the left to the y-axis on the right. The output of the first becomes the input of the second, and even it's still there, but it is cumbersome and not very revealing of what actually is going on. And what's going on is not really that complicated. It is just a consecutive application of two operations, predetermined operations. Okay, so it's especially simple when you're facing something like that, what we talked about last week. Earlier this week, it is like transformations of the x-axis. You transform the x-axis into the y-axis by a stretch, and then you transform the y-axis into the z-axis by another stretch, and you can combine them together, and that's also going to be a stretch. And but just the factor changes from 2 and 3, it becomes 6. And then you can combine any kind of two transformation of that nature. You can have a fold, you can have a shrink, you can have a shift, as well as non-uniform shift stretches and so on. Okay, so think about another way to think about is a transformation of something other than numbers, an assembly line. Okay, and so you do add things, do things to an object or say a car, and you progress from one to the next, and you cannot jump to the second step before you carry out the first. The number of steps could be unlimited, but they all. The point is that they are carried out in a consecutive manner. Okay, so that's the idea of transformation, which explains what it is. The order of operations matter. That's an example of a simplistic example at the bottom, which is it doesn't matter which stretch you do first, 2 or then 3, or first 3 then 2. It doesn't matter. But if it is assembly line, if it is a lot of other operations, it does matter. For example, stretch and shrink. Stretch and shift would not be the same as shift and stretch. Okay, so well, you probably can see that example. But later on, the second point of view that we have to inevitably come back to numbers, inevitably come back to algebra. So what is the compositions, the point of compositions in the algebra setting, and that is substitution. So you know which function comes first, which second. The first function is substituted into the second. Okay, so that is what's behind the notation of with all of those parentheses, which is here somewhere at the bottom. Okay, so that's what this meaning is. F is inside of G. If you read the thing inside out, you can recover all the diagrams that we have had. It is in that little notation. So it is from x, what we're reading here is from x to f of x, which is y, and then from y to g of y, which is z, the final step. So that's all is visible in this notation. Okay, so it's a three-step, a two-step operation. Input x, f is applied, you get the intermediate value of y, y substituted into g, and you have the answer. Specific examples are right there, how the substitution is carried out. Okay, so and then the what's on the left is the notation that we commonly use for the composition. It's a little circle, and it goes it's just one name for the whole thing, so it goes straight from x to z. This is G circle F. Okay, so as I said, the substitution is this new operation that you can carry out with numbers. Functions you cannot carry it out with numbers. Okay, so numbers we have those 4 operations of algebra, but this is like algebra of functions rather than numbers. Okay, so and then that's what we got to last time at the end. The opposite problem. So the original problem is substitution. The opposite problem is decomposition. So you have a function and you decompose it into consecutive steps. Okay, so that's an example. 1 over x cubed, and you don't want to do any kind of manipulation of algebra in order to avoid solving the problem as it is posed. Sometimes you can, but there is just no point because it is meant to illustrate the idea and to simplify the computation. The challenge is to begin with to understand what the function does. What the function does, if you know what the function does, then you can figure out, you will inevitably arrive to the conclusion that it is carried out in a number of consecutive steps. And then the challenge is to recognize each step as a separate function. Okay, so that's if you think about this is what we try to understand what the function does is here. So if you're not sure, just plug in a value and see how far it takes you. So if you plug in 3, how do you find the outcome? You first take 3 to the 3rd power, gives you 27, then you flip it, and the reciprocal is 1 over 27. That is the answer, z. Okay, from x to z in 2 steps, and then you just describe those steps so that they will be applicable. So in some, probably verbal is fine early on. Describe it in such a way that you could carry that out, these 2 steps, with any number that is given to you. So x is given, and then you proceed with these 2 steps. First, cube it, and second, the output of that is put into the second step, which is take the reciprocal. Okay, so the algebra is there, and you can now introduce variables in order to formalize this. There is actually no problem with this description. It is complete. If you give it to somebody, the person would know what to do, even though there is no algebra. Just this is the description. X is given to you, cube it, take reciprocal. So hypothetically, you can think about as you are a boss, and you have a task to be carried out. You carried out this function. So then you have one person that will be responsible for cubing it, and the other one is responsible for doing the reciprocal. Okay, so and then that's what you do as a manager. You distribute the tasks and arrange them in a proper way. So the first guy will not know what the second guy does. You'll tell him, this is you, the first guy. I'll give you a number, you cube it. Okay, then you pass that number that you got to the next guy. So you Smith, so you pass it to Jones, and Jones Jones, you will take the reciprocal of what you get from Smith. Okay, and then the result, pass it to me. You might not know anything about how to cube it. You might not have no idea how to do these operations, but you split it apart and give it. That's what the manager does. To your people, and then now you can actually carry out that function seamlessly, and that was your job, to make it seamless, which creates a challenge even before we get to algebra, which would be actually up to those 2 people to use or not to use algebra. But you as a manager, what challenges you would be facing is to be able to pass along like I said, seamlessly. And what is seamlessness? Seamlessness, if not knowing the domain and the range. So you should know ahead of time what kind of values you're going to be plugged. You are allowed to give to the first person because the cubing a number, the domain of the cube of the first step, cubing is actually all real numbers, which means that that person will be unconcerned with what he's going to produce. So, but you have to not give that person a number, what number that is not allowed. What's the number not allowed? 0 is not allowed. So you as the designer of the system, which you maybe talk to deal with people or work for you, or maybe those computers, so that doesn't matter. It is up to you to figure out ahead of time so that you wouldn't do a thing that would break the whole thing apart. So you have to actually trace back, look at the step 2, and figure out its domain. So domain is x not equal to 0, and then pass it backwards to the step 1 to understand that what number not to give to the first person, okay, which will be once again, well, x not equal to 0, probably better put y not equal to 0, because that is our variable, the intermediate variable, okay, and then that requirement that y cannot be equal to 0 translated backwardly to the domain of the first, not of the first function, but of the whole function, and that of h, and that is x not equal to 0. Okay, so then this is domain of g. That's what the second function does. It does division, so you know that you not supposed to give that function y equals 0. Okay, so but then you pretty much have to work with the first guy to figure out what is that what happens inside of that little black box, so that the 0 would not be given to the second guy. So even though you're not doing everything every time, but if you want to set it up properly ahead of time, you do figure out the domain and domain of the original function. And it turns out the answer is 0, so that is how you would be dealing with this function. You would say, well, here's the domain h of the function h of the whole thing, x not equal to 0. Okay, so that always will come up. The domain will always come up. But in the meantime, what the second stage possibly of this problem would be, or likely, is to now algebraically, you have to present these functions algebraically. They're all there in the box. So the big box of h and 2 boxes, 2 consecutive steps inside of it. And so just you present the functions appropriately. Just how do I get y? I get from x, I go to y, which is what is it? Cubed. So it's x cubed. Call it y. Okay. Then y is passed to the next stage. And what I do, I take a 1 over y, which is z. Okay. So that's the 2-step procedure. At the end, I end up with a z. These are the 2 functions. So this is the first stage is f, second stage is g, and well, that ends it. So that problem, the problem represent as the composition we have. The only thing that's missing, that might be if you want to write the answer, you want to. So this is like analysis, and then you write the answer as specifically. So y is equal to f of x equal to x cubed. Okay, z is equal to g of y is equal to 1 over y. Okay, so that is it. And then implied assumption here is that the order of things also should be part of the answer, even though it is implied here, like it is really unambiguous. You know, once you wrote your variables properly, you know which ones substitute where, so you know that f will come first and g second. But just to verify that you know how it's done, you write it like this. Our function h is g circle f. Okay, so that's part of the answer. So you identify the function. So the task was to represent h as a composition. You pointed out not just pointed out the function, you gave their formulas, and you pointed out in which order they're being carried out. Okay, so that's the typical problem for about compositions. 2, we have now either you have two functions given and you have to combine them and produce one formula, or you decompose it. The variety of problems, however, might be big, and let me do one more of this kind first, or the previous kind rather. So composing and decomposing, these are two sides of the same coin. Okay. Sometimes that's what you're going to see in the next homework, I presume. Since it is typically not to. Well, let me show you the problem that we faced last time. The original, the composing problem. It is very straightforward. Substitute one into the other, but it's only straightforward when the variables are taken care of. So x and y, as you can see, intentionally is written in such a way that you know which ones go where. So x is substituted in place of y, and then you know what happens. So that's that's unfortunately not a typical situation. More typical situation would be like this. You have to figure that out. So find the composition of f of x is equal to 1 over x plus 1, and g of x is, I don't know, sine x. Once again, imagine you don't know what sine is. You don't care. You don't care. Once again, if you have people who know how to handle sine, and you just pass along that job to them. Your responsibility as that who designs everything is to know, first of all, that sine is a function, and so that is the problem to be dealt with, and also take care of the domain. Otherwise, you don't really need to know what sine is. You're just combining things together and then see what happens. It is like the delegation, So you don't know exactly. If you have people laying bricks for you, you don't have to lay bricks anymore because people do it for you. But you just have to do the rest. Okay, so combining, and there you see the ambiguity of the statement. What's the problem with the statement? With the requirement? Two functions, we need to find their composition. There is some problem with the way it's worded. Well, the variable, right? Well, that too. We have one variable, x, and it is the same for both f and g. So what does it tell you, or not tell you? Yeah. Okay. Well, you remember that when you compute the composition, you substitute one function into the other. Which one? Which one?
G substituted into F.
Why is that way, not the other way around? Well, I'm saying it was a trick question, but the answer is that we don't know. That's the that is the problem with this wording. Unfortunately, you're going to see it in the next homework.
So you can do either substituting.
Yes, that's right. If it is put this way, then you have to figure out either do one or the other or both, depending on the circumstances. When you just say find the composition, it is ambiguous. So you don't know, and then so there are two questions behind this, behind one, and so it's either one is substituted into the other or vice versa. So so you just decide which goes F then G, or vice versa. So case 1, case 2, solve them separately. How I would suggest, even though you probably can do it quickly and just from intuition, or I would suggest take care of the variables. So I rename the variables. for the purpose of knowing where the substitution is going to be. So before you start doing any substitution, you sort of align things just right, so you know where it goes. So in which way you just make the the output of the first called y, or whatever that is. So y is the output of the first, which is, as you can see in the original statement, is not present. Y is not present, nor z. So we know that we're supposed to go, and that's probably a good idea, from x to y to z. Okay, and we just have to decide, is it f then g, or it is g then f. Okay, so once again, two cases, and case one is, this is case one, and this is case two. The same sequence of variables, probably, for your own convenience, but certainly the answers will be very different. Okay, so y is the output of the first function. So then if I now do in case one, I will have then f comes first, so its output is y, and I have y is equal to 1 over x plus 1. Then y is the output of the first function. It also means that it's also the input of the second. Okay, so what's the second function then? The second function is g, so no, rename.
And the output missing.
Yes, z is equal to sine y. Okay, so that creates a match between the output of the first one and the input of the second. Okay, and then you know that one will be substituted into the second, and then you have your answer, right? So you have z is equal to sine of 1 over x plus 1, and that's the answer. Okay, as you can see, whatever we're introducing y, renaming everything, that even though it has been done, it in the final answer, it's not visible as intended. So you solve the problem as it was posed to you, and all these steps you took, even though if you're writing, you certainly have to present them, but if you only need the answer is appropriately answered the question that was posed originally. Okay, case two. So what do I do? Output, y is the output of the first function. This time the first function is g. Okay, so I have, so y is equal to what? Sine x, yes. And z is?
1 over sine x plus 1.
No, y plus 1. So once again, we have output of the first is the input of the second. Once again, we have substitute. We substitute. What do we get? We get, as planned, we have the new answer. Z is equal to 1 over sine x plus 1. Okay, so as you can see, there is really no relation, or at least on the surface, these are two very different functions because the order matters. So we solved two problems in one because we could substitute one into the other, or vice versa, and the answer is typically to be expected to be different. Any questions about this? Okay, so algebra, transformations. We'll talk more about transformations later. There's another angle of speaking of functions, and that is what if the functions are given by their values, no formulas. So there is no, in the literal sense, there is no substitutions. So functions given by tables of values. So the idea is the same, but there is not literally, we're not substituting anything. So let me try. So x and y, I will take care of the variables early on, so there would be no doubt, even though sometimes, well, let me try to, no, okay, so just keep it. So the two x variables, x and y, these are the inputs of the first one. 1, 0, 2, 4, 2. Okay. The first function, let's say f. So x input, y output. Okay. Now, so far unrelated. The second function, say g. But I will look ahead. Well, let me give the values first. 0, 1, 2, 3, 4. 0, 3. 5, 1, 2. Okay, so certainly that qualifies as a new function, but if we want to speak of compositions, and we do, we want once again align variables, and I will use for the first column, use the same letter as for the second column of the first function, so they are aligned. The output is this is the output of the first function. This is the input of the second function. So they will be aligned. They are rather matched, but not aligned. So that's the only challenge right now is that these two columns are not the same. They consist of the same numbers. As you can see, they run between 0 and 4, but they are not aligned. But that's okay. So then I also named the third variable here z. So that will be the output of what? Of the composition. So I put that circle over there to indicate that we have two functions, and now we want to produce a composition. Okay. So okay, so it is a table. What's the name of the first column? X, and of the second? Z, yeah. Okay, the name of the table is, by the way, it is a composition, so if it is FG or GF. F, no, G circle F. Reading from right to left. Okay, so now the x's are given, so I'll just take this. These are my x's, and I will copy them just so that there would be no ambiguity here. I will stick to the same values. Okay, so these are my x's, and now the corresponding values of z are to be found. Okay, so this is my z. That's where it came from. Okay, so how do I do it? I just follow the arrows. The arrows that the arrows are implied in each of the tables. 0 corresponds to 1, 1 to 0, 2 to 2, 3 to 4. These are the arrows of the first function. It's what we started with the arrows, but in the table those arrows are implied. Okay, and then so then I have to answer 5 questions. What is the value of 0 under this new function? How? I carry out 2 consecutive steps. So, okay, so what's the value of 0?
Is it still 0?
No,
3.
it is 3. Can you explain?
Because on F, 0 equals dx, which is 0, would equal 1 for y, and on G, y, or where 1 is, it equals z as 3.
Yes. So it is like a substitution, except it's kind of implicit. So, but you have to match up the output of the first with the input of the second. So if the output is 1, you need to find that value in the column, in the first column of the second function. Then you know the output, which is 3. Okay, so that's the result of the very first computation. 1 goes to 3. And then I'll do it as many times as necessary. So 1 goes to 0. I need to find 0 We find 0. So the 0 is the output of the first step. I find the 0 as the input of the second step. So this is my next step. So find 0. If I found 0 in this column, y column, I need to find that 0 in the new column, which it might be misaligned. As you can see, that's the problem, because x's and y's in these two tables are arranged in the chronological order, in the growing order, as you would always do when you have a table of a function. But then the values of a function, the second column, might be random. So that's why you have a misalignment. Anyway, and then you end up with 0, right? And then, well, let me do more of it. 2 goes to 2. Then I find that the 2 on this side. So find 2. Okay, 2 goes to 5, and so 5. And the answer is 5. 3 goes to 4. I find a 4. And 4 goes to 2, so the beginning and the end, whatever that 4 in the middle doesn't matter anymore. 3 goes to 2. Okay, one more. 4 goes to 2. I find the 2 over here. And so then the answer is 5. Okay? So that's another typical problem of this kind for compositions when there is no formula, there is no graph, there is no description of a transformation. So it's in numbers, and just you need to follow the arrows. As you can see, the arrows are not parallel in the sense that we have done before. In fact, probably. I think we may have done this before. I can't exactly remember, but just to compare, or rather to contrast this, this is how you compute the composition. This is how you compute the other operations, which we may have done before. Maybe work out. So just to refresh your memory, did we do this before? Addition of functions. Did we do addition of functions? If we didn't, let me put it here. So to see how easy it is to add functions. Okay, so add functions. FG, so the same functions. Like this, so same functions altogether. Okay, but now what I want to do is I want to add these two functions. It's another operation on functions that is in fact definitely simpler than the original. So I'm talking about f plus g. Okay, so how do I do it? That is really simple. I just go along this way, like this. Every single time I just go horizontally. So the input is the same. So in fact, I have to rename the variables in order for things to match up. The input is in either case is in fact x. The output for both of the functions in either case is y. And you can say that the output is also of the sum of the two functions is also y. Okay, so that's how you add functions. So what do I get? 0 goes to 1, 0 goes to 0. So it's 1 plus 0 is equal to 1. Then along the second line, I have 0 and 3. 4. The next line, I have 2 and 5 is 7. 4 and 1 is 5. And I have 2 plus 2 is 4. Okay, so that's very simple when it is about addition. So this is addition of functions. Compare and contrast, if you like. Well, that's how we would code. So a composition of functions. If you just put these two side by side, how you add and and compose functions that are given by tables. That's how different it is. Adding, this is especially, you probably can do it easily with a spreadsheet. You enter the data and then you enter this little formula that adding the output of the two functions together. So as you can see, that's where that new column that we discovered, that's y over here, has been found. You take two y's and add them together. Okay, 1 plus 0, 0 plus 3, it's 0 plus 3, I'm sorry. 0 plus 3 over here is 3. Okay, so that is the addition of functions. Same with subtraction of functions. Same with multiplication of functions. Same with division of functions. You go horizontally. Because x's are the same and they are already aligned. Both of the in that case, x's are the input variables, and so that if they are aligned, that the two functions are aligned and they are computed one at a time. The compositions, as you can see there, they're more complex in that sense. You have to actually do a search. And if you try to do it with Excel, that actually does require exactly that. You have to do a search through the second column. What we did it by hand because it's so small. You need to find that one in order to know where you end up. So the output of the first function, it's like it points you in which way to go, roughly. It doesn't give you a number to do algebra with it. Okay, so it's in that sense it is very different from algebraic operations. So composition here, addition there. Very different if you look at them side by side. So not to be confused. Okay, maybe one more example of this kind. Slightly trickier. So decompose informally, what it means is represented the composition. Okay, the function is say 2 sine cube x plus sine x plus 5. Once again, if you don't know what sine is, you don't care. All you need to know is that it's a function. Okay, it's a function x. The output sine is the name of the function. You can just as well think about sine as maybe it's a sin, not sine. That doesn't make any difference. Okay, so decompose it into two-step procedure. So this is slightly different because here it is definitely going to be about sine, but sine appears twice. Okay, different from what we have seen before. So what difference does it make? It makes it means that the first step is still the same. Step 1 is compute sine. Y equals sine x. Okay, and then it is substituted in two different locations. And you know what sine cubed means. Sine 3x means sine x cubed. That if you've seen trigonometry before, that's the common way to put it, even though it is slightly misleading. So that 3 squeeze between sine and x, it is in fact you first compute sine and then you take the cube of it. So it is in fact that sine cube x is a composition of its own. Okay, but now we just have this step to be carried out, and it is being fed into two different locations in my new function. So what is the second function? So think about reverse substitution. So you know that if you have a function, you are trying to think of a function in terms of y, so that when you replace each y with sine x, you're going to get that formula. So that's how you have. It is almost literally also substitution, except kind of you replace something more complicated with something more simpler. So sine x replaced with y. So let's take that formula and replace each sine x with y. What do we get?
Would it be 2y cubed plus y plus 5?
That's right. 2y cubed plus y plus 5. Okay, so if unsure to test, do the back substitution. Or just literal substitution. So you know that y is supposed to replace that expression that we have, and you just verify that it works out. So in other words, you combine these two, and what you have is z is equal to 2y cubed plus y plus 5. Replace each y with a sine. Okay, so we have sine x here, sine x there. And then what it's surrounded by is 2y cubed plus y plus 5. Okay, so that's my substitution, and indeed that checks out. We end up with the same expression as the original. Okay. Okay, so this is the composition, how composition work out. So we'll continue doing it because it's such a central concept. And there is a whole thing about algebra of compositions and how we have combine multiple functions in a row. But we'll let it settle a little bit and take a concept that again about geometry and what happens to graphs. So this is the question: what happens to graphs under compositions? Some compositions. Specifically, what this is about is replacing, producing new functions from mold. Say, if I have y equal f of x, and then we know it's graph. Graph is known. Let's say something simple. Okay, and then we are making up a new function. Say y is equal to 3f of x. And then what is its graph? Okay. You should think about it as of this expression as a composition. A composition of your function f, which is unspecified at this time, and what else? And what else? Oh, actually, how about I put a z here? Composition of f with what? Not 3. If you say 3 is your function, then it is 3 it is a constant function. So whatever comes out is 3. So which is probably more worth mentioning. Remember, say you have some kind of function. Okay, so f, and then you have the next function is 3. It means that everything adds up at 3. That's what a constant function does. It produces constant output no matter what the input is. So this is not it. This is slightly more complicated, even though this is certainly an example to be remembered. So it's not 3, but what?
3 times the function.
3 times, yeah. So in other words, it is z equal 3y. Okay, so that's a composition. You can see if you just replace y, f of x with y, or y with f of x, you have that function. Okay, so that's a composition, and then the question is, so what would the graph of the new function look like? You want to guess? You can guess based on what? Based on the nature, and that I'm taking you back. What is the nature of this transformation? What is this? When we multiply by 3, what is it? It's a stretch, right? So stretch. So in other words, the y-axis is stretched by a factor of 3 before it becomes the z-axis. So if you stretch the y-axis, then the full xy plane will also stretch, right? So literally, and so the graph, what will the graph look like? So stretch by 3, and stretch by 3 of what? Of the y-axis, which causes then the xy plane is stretched vertically by a factor of 3. So this is my y-axis, which is stretched into z-axis. Okay, nothing happens to the x-axis, right? So x is intact, the same input, but the output becomes 3 times. Okay, so that's what we talked about not a long time ago about stretches of the axes. Okay, so that's a different story here because now we are by stretching one axis, we actually stretching the whole plane, right? So because you think of it as a piece of rubber, and we are not pulling y-axis by itself, but rather every vertical line here gets stretched. So these lines are also stretched. All of these are stretched in the vertical direction by a factor of 3. So instead of thinking about a piece of rubber stretched like this, you think of a sheet of rubber stretched like that. Okay, so imagine a piece of rubber with that parabola drawn on it. If you stretch it, what does it look like? Piece of rubber, so a sheet of rubber with this picture drawn on it, and then I'm pulling it. I grab it not by a point like this. I'm grabbing by the whole thing and pull it like this. What happens to the parabola? Yeah. So can you describe it? Well, nothing happens to the horizontal. It is pure vertical stretch. So it will become slimmer. Like this, okay. So we'll talk about that next time.